Now we started first mini course. We have 2 mini courses. Then today we start the first one with Carlos Augusto Bassani Varea. First of all, thanks for accepting our invitation, Carlos.
Thank you for the invitation.
Carlos has got a degree at math at Maringá, 2013, and then he moved to Unicamp and he did his master's. And last year he got his PhD, and now he's actually has a postdoc position at IME, in USP, São Paulo. And till now, he have published 5 articles. Since, although a young researcher, he's has 5 published articles, and we'll be giving 3 lectures about generalized complex structures on flag manifolds. We have this first class today, lecture today, and the other ones will be on last Friday, and in the last one on next Wednesday, in the last day of the event. So, Carlos, thank you again, and you keep doing your lecture now.
Thank you, Leonardo. I will let's start thanking the organizers for the invitation to give this mini course. It's my first time teaching in a mini course, so I hope you enjoy it. The title is Generalized Complex Structures on Flag Manifold. It's part of my PhD thesis, which I was supervised by Luis San Martin. So this is a joint work with Luis San Martin. So the idea of this mini course is this one. So today, in the first lecture, I will present some preliminary concepts. So I will talk about generalized complex structures, and I will basically fix some notations on flag manifolds. Okay, and for the other days, on the second day, I will talk about our description of the generalized complex structures on flag manifold without asking about integrability. And in the last day, we will study the integrability of such structures. Okay? This concept of generalized complex structures was introduced by Nigel Hitching in 2002 in his article called Generalized Calabial Manifolds. And initially, it was developed, this theory was developed by Marco Gualtieri in his PhD thesis. He was supervised by Hitching. And one of the advantages of this generalized geometry is that it allows us to study complex and symplectic geometry in a unique framework. So I didn't say it in the first, but since it's a mini course, not a plenary or a talk, you can stop me at any time and ask questions. Okay, don't need to do it only on the final of the talk. So in the same way as we do when we are studying complex or symplectic geometry at the first time, I will present the notions of generalized complex structures on a vector space, and then we will generalize it for smooth manifolds. Okay, so let us consider V a real vector space, finite dimensional, and by V star we will denote its dual. So just to remember, we define a complex structure on a vector space as a linear map satisfying this condition that J square is -1. Okay, and a symplectic structure is defined as a non-degenerated 2 form on V star. Okay, so observe that a complex structure is defined on the vector space V, and a symplectic form is defined on the dual space. So if we want to study complex and symplectic structures in the same framework, we need a bigger space that contains V and V star. So this is why we are going to work in the space V plus V star. Okay, so this is the space that we are going to work all the mini course. And this space, V plus V star, is endowed with the following bilinear form, given by this expression here. And this is a bilinear form that we are going to use throughout all the mini course, so it's important you remember this expression, okay? Okay, so we can define then a generalized complex structure on V as an endomorphism on the space V plus V star, satisfying two conditions: a complex condition saying that J square is -1, and a symplectic condition saying that J star is -J. In other words, we can say that J is a complex structure on the space V plus V star, satisfying the condition that is orthogonal with respect to that bilinear form, to this bilinear form here. Okay, so you can think in these two ways. Okay, and the first, I will present two examples here, one that comes from complex and one that comes from symplectic geometry. So first, this one that comes from complex structures. So let us consider J a complex structure on the vector space V, and we will define by this calligraphic J of J this endomorphism on V plus V star, with given by this expression here, -J in the first component and J star in the last one. Okay? So we will prove that this is actually a complex structure. So we need to prove two conditions: that J square is -1 and that J is orthogonal with respect to that bilinear form. Okay? The first condition is an immediate consequence of J being a complex structure. So since J is a complex structure, J square is -1. So when we compute this calligraphic J of J square, you can easily conclude that it's also -1. Okay? So the other condition is to prove that this is orthogonal. It means that we need to prove that this is actually satisfy this condition here. Okay? So J of C plus X plus C, applying the bilinear form of J with I plus eta, is actually this other guy here. Okay? So this is what we need to prove here. Okay, so when we write this J of X plus C, we are going to use the matricial form. So the form of J of calligraphic J of J is given by this expression here. So when we apply on X plus C, is just doing the product of matrix by a vector X plus C. Okay, so just doing the product here, we obtain this expression here, which is actually this guy on here. Okay, so applying this guy here is just doing this product, so we are going to have this expression, and the same on the second entry. So when we compute this, we have this expression. And now we apply the definition of the bilinear form. So it's going to be half of the vector part, the dual part here, applied on the vector part here, plus the dual part here, applied on the vector part here, vectorial part here. Okay, just the definition. And J star of C is just C of j applied on this guy here, and the same on the second entry. Okay, but observe that here appears j square, but j is a complex structure, so j square is -1, and the same is happening here. We have here j square, which is -1. So we obtain actually c of y plus eta of x out of this, and this is exactly the definition of the linear form. So we proved that calligraphic J is orthogonal with respect to the linear form, and then we can conclude that J is actually a generalized complex structure on V. Okay, so some computations, but it's quite easy to see that J of J is actually a generalized complex structure. In the same way, we have the second example, where is given when we have omega, a symplectic structure, we can induce a generalized complex structure on V given by this expression here. Okay, and to prove that this is actually a generalized complex structure is quite similar to the previous one, so I will let it as an exercise. Okay, so this is the first two examples that appear in the literature of generalized complex geometry, and in some, maybe a lot of cases, the only two examples that appear, and they are important examples because are the examples that we recover the complex and then symplectic geometry in this language of generalized complex structures. Okay, so this is the two examples that we are going to use in today. Okay, so but we have another way to look for the generalized complex structure. The first one was using endomorphism, satisfying those two conditions. But we have another one, which is given by means of isotropic subspace. So just to remember, subspace L is isotropic when satisfying this condition here, where here is the bilinear form that I defined first. Okay, this means that a subspace is isotropic when L is a subset of its perpendicular. Okay? Because of this, the dimension of an isotropic space is less or equal to the dimension of the space V. So we are going to say that an isotropic subspace is maximal when it has exactly the dimension of the space V. In our case, it's N. Okay? And we also can define the type of an isotropic subspace as the codimension of its projection onto V. So we have an isotropic subspace, we will project it on V, and then we will compute the codimension of this guy here. Okay? So it's the dimension of V minus this. This is the type of an isotropic space. Okay? And the proposition that relate these two notions is this one that you can find on the Gautier's thesis. It says that a generalized complex structure is equivalent to a maximal isotropic subspace L, no longer on V plus V star, but now in the complexification of this space, satisfying the condition of real index 0, which means that satisfying this condition here. Okay, the definition of real index, the real index is the dimension of this intersection here, where this bar is the conjugate of L, okay? And so, work with generalized complex structure, we have now two ways to look at it, as an endomorphism or as a maximal isotropic subspace, okay? If you So this is the proposition that relates these two notions, the notion of generalized complex structure with maximal isotropic subspace. And it's given by this proposition that you can find on Gualtieri's thesis. And if you look the proposition, the proof of the proposition, if you take a look in the proof, you see that when you take a generalized complex structure, which means an endomorphism on the space V plus V star, satisfying those two conditions, then this maximal isotropic subspace that you are going to relate is the IL will be the I eigenspace of J. The I eigenspace of J. And reciprocally, when you take a maximal isotropic subspace, you can prove that this maximal isotropic subspace is actually the I eigenspace of some endomorphism satisfying some generalized complex structure. Okay, so this maximal isotropic subspace that relates the notion with the generalized complex structure is actually the I eigenspace of the generalized complex structure. Okay, so now we have two ways to study generalized complex structure by means of an endomorphism satisfying two conditions, a complex and a symplectic condition, and by means of an maximal isotropic subspace satisfying this condition of real index 0. Okay, so we have these two equivalent notions. Okay, and we will say the type. So we define it before, the type of an isotropic space. So we can define the type of a generalized complex structure as the type of its I eigenspace. Okay? And if we back to the example, the second example that I gave, which was the generalized complex structure which comes from a symplectic structure, defined by this expression here. If you compute the I eigenspace of this structure, you will get this subspace here. So we can prove that we can compute the type of this structure. So the type is the codimension of the projection onto V. So if we compute the projection onto V of L omega, given by this expression, but observe that we are running all the X which lies on V. So this projection is actually the entire V, okay? So the codimension of this projection will be 0. So the generalized complex structure which comes from a symplectic structure is of type 0. Is one extremal case. And the other example is the generalized complex structure that comes from a complex structure. And it's the other extremal case. You can check that the type of this structure is equal to the dimension of V. Okay, so these are the two extremal cases, 0 and M. Okay, and as I said in the beginning of the talk, we start studying this notion on a vector space, and then we can extend this notion to smooth manifolds. Okay, so let's consider M a smooth manifold. So we can define a generalized almost complex structure on M as one of these two equivalent data. So we can define as endomorphism on the tangent plus the cotangent space, which is called the generalized tangent bundle, sorry, not space, bundle, is defined on the tangent plus the cotangent bundle, satisfying those two conditions, that j squared is -1 and j star is -j. Or, equivalently, we can define it as a maximal-isotropic subbundle on the complexification of this tangent plus the cotangent bundle, satisfying the condition of real index 0. Okay. We also have another equivalent definition of generalized complex structure, and it's about pure spinor line bundles. But we are not entering details in this because we are not going to use. But if you want to see with more detail this definition, you can look at the Gautier's thesis, okay? So if you pay attention here, when we extend the notion of generalized complex structure to a smooth manifold, appear this word almost here. So we can think in some kind of integrability for these structures. Okay. Well, when we are working on complex geometry, we have that an almost complex structure is integrable if and only if the Nienhaus tensor vanishes. Okay. When we have omega, a non-degenerated true form, omega is symplectic if and only if omega is closed. And if you go deep in details of these guys here, you can conclude that the Nienhaus tensor depends directly on the Lie bracket, and also when you compute the derivative of two form, you also depend on the Lie bracket. But so the Lie bracket is directly related to the integrability conditions in complex and symplectic structures. The problem here is that the Lie bracket is defined only on smooth sections of the tangent bundle, and we need something also on the cotangent bundle. And this is where appear the Courant bracket. Okay, so the Courant bracket is a skew-symmetric bracket defined on the smooth sections of the tangent plus the cotangent bundle, given by this expression here. So, where on the right-hand side we have, I will denote with in the same way here. Here on the left-hand side is the notation for the Courant bracket, and on the right-hand side, this first term denotes the Lie bracket of vector fields, okay? And this calligraphic L denotes the Lie derivative, okay? So this is a bracket defined on the sections of the tangent plus the cotangent bundle. So we are able to give a definition, a notion of integrability for this generalized complex structure. And this notion is the following. We are going to say that a generalized almost complex structure, J, is integrable, or we are just say that J is a generalized complex structure when its eigenbundle, L, is involutive with respect to the Courant bracket. Okay? Okay. So to check this notion of integrability, we check in the two examples that we are using in this talk. Okay, so when we consider the generalized complex structure, the generalized almost complex structure given by an almost complex structure, given by this expression here, one can prove that this calligraphic J is integrable if and only if J is integrable in the sense of complex structure. Okay? In the same way, when we consider a generalized almost complex structure that comes from a non-degenerated 2 form, J given by this expression here, J omega. So J omega will be integrable if and only if omega is actually a symplectic form. Okay, so it means that this notion of integrability given by the Coulomb bracket is a really good notion because it recovers or it agrees with the definition of integrability in the complex case and in the symplectic case. Okay? We actually have another way to look the integrability, and it's by means of the Nienhaus operator, where the Nienhaus operator is defined by this expression here. Okay, where on the right-hand side, we have that bilinear form defined in the beginning of the talk, and here we have the Coulomb bracket. Okay, and we run all the cyclic permutations of these three elements. Okay, and the proposition that relates this notion of integrability is that we say that J is integrable if and only if the Nienhaus operator vanishes when we restrict to the I eigenbundle of J. Okay, so look, the involutive of a structure it might not be so easy. So here we have an operator which become easier to work. Okay, so in my work with Professor Luisa Martin, we used this notion to this operator to look the integrability of these structures. Okay, and basically it's all we need of generalized geometry to study the generalized complex structures on flag manifolds. Okay, so now I will basically fix some notations on flag manifold because I'm supposing that you already know about flag manifolds. Okay, so I just fix notations to you. So I will denote by G a semi-simple Lie algebra, and this G over tilde because I'm I'm not able to do this Gothic letter as in the books G, so I will use the notation that I learned with San Martin, this G with a tilde below. So G will denote a semi-simple Lie algebra, and by capital G we will denote the Lie group associated with Lie algebra G. We will consider H a Cartan subalgebra, and then we can decompose G in terms of the root spaces, G alpha, where pi here, pi is the set of roots of the Lie algebra G. Okay? For each alpha, we can define a unique element H alpha, which is defined by this expression here. And the set of the spanned by these elements H alpha, we will denote by HR, the real spanned. And we will fix a Weyl basis, which is actually elements X alpha satisfying some conditions. Okay? I will use also this notation for the killing form. I think there is no confusion because of the context. So the Weyl base satisfies the condition that the killing form between X alpha and X minus alpha is 1, and satisfy some conditions on the Lie bracket of two elements, which is this one when alpha plus beta is a root, and is 0 when alpha plus beta is not a root. Okay, so this is a Weyl basis. We will also denote by pi plus the set of positive roots, and by sigma the corresponding simple root system. So with this notation, we can define a Borel subalgebra, which is given by the Cartan subalgebra plus the root space associated to positive roots. Okay, and once we have the Borel subalgebra, we can define a parabolic subalgebra as a subalgebra P satisfying the condition that the Borel subalgebra is contained on P. Okay, all of this notation because we want to define a flag manifold, which is defined as the homogeneous space G over P, where P is the normalizer of a parabolic subalgebra. Okay, so this is the notion of flag manifold that we use here. Specifically, when the parabolic subalgebra is exactly the Borel subalgebra, we call the flag manifold as a maximal flag manifold. Otherwise, it's called a partial flag manifold. Okay, and I didn't mention this in the beginning of the talk, but I will work only with maximal flag manifolds. Okay, in the final of the mini course, I can explain why I don't work with partial flag manifolds, but for us in this mini course, when I say a flag manifold, I will mention a maximal flag manifold. Okay? Okay, so we have another way to look at the flag manifold, and it's using a compact real form. So let's take U, the compact real form of G defined by this expression here. Okay, where A alpha and S alpha are these elements here defined like this. So we can, if we consider U the corresponding compact real form of G, so we can prove that F, the flag manifold, can be identified with U over a maximal torus of U. Okay? As I said, here I'm considering F a maximal flag manifold. When we consider a partial flag manifold, we actually have U over a centralizer of a torus. Okay, but for us, it will be always maximal flag manifold, so it's U under a maximal torus of U. Okay? Okay, so let's consider F a maximal flag manifold. So since U is a compact Lie group, we have that the homogeneous space is reductive. So we can decompose the Lie algebra of U. It means that we can decompose the Lie algebra of U as the Lie algebra of T plus its orthogonal complement that we will denote by M. So if we look at the construction of the compact real form U, given here, we have that this M is the sum of which we are going to call by U alpha, where each U alpha is the real generated, real spanned by the elements A alpha and S alpha. Okay, and also since F is a reductive homogeneous space, we have an isomorphism between the tangent space at the origin of the flag with this space M given here by this expression here. Okay, so this is the tangent space at the origin of the flag. Okay, so the main goal of this mini course is to describe the invariant generalized complex structures on F. Okay, and when I say invariant here, I mean invariant under the isotropy representation. Okay, but since we are working with a reductive homogeneous space, we can identify the isotropy representation with the adjoint representation. Okay, so when I say invariant, I mean invariant under the isotropy representation, but here for us it's invariant under the isotropy representation. Okay, and since we are working in the tangent plus the cotangent bundle, the adjoint representation is actually the direct sum of the adjoint plus the coadjoint representation. Okay, and also I think you all know when we work with invariant objects in here, we can reduce the problem to at the origin. Okay, so instead of working in the tangent bundle plus the cotangent bundle, we are working with the tangent space at the origin plus the cotangent space at the origin. Okay, which we can identify with the m plus m star. Or equivalently, so describing the invariant generalized complex structure in this space here is equivalent to describing the maximal isotropic subspace in the complexification of this guy. Okay, so for us, the idea is to describe this subspace. So just to finish today, I will let you with this proposition, which is really important for the next lecture, okay? This proposition is saying that a maximal isotropic subspace on M plus M star, so a maximal isotropic subspace here can be decomposed in terms of the roots of the Lie algebra. And this guy will be maximal isotropic if and only if each part, each L alpha of this is maximal isotropic inside this space here. Okay, so this is a key proposition for what comes next on next lecture. Okay, so I will stop here. If you had some question, that's it. Thank you.
Okay, thank you. If one has any question to Carlos about this first lecture. Okay, okay, can you go back to page one, please? Daniel is asking.
Page one or one page?
Oh yeah, one page here.
One page,
yeah. One page, yeah.
This one? Okay.
So I have a general question about this generalized complex geometry. As you said, started 2001 and
2002.
2002. Yeah, but
yes.
You applied to the context of flag manifolds only now. The theory was applied to flag manifolds only, and when you started to work with these things. Or is there some previous work on flag manifolds and generalized complex geometry between this time?
Yes, there's a work of Brett Milburn where he studies some generalized complex structures on homogeneous space. But you will see in the next lectures that we gave an explicit expression for these structures, and he just guaranteed the existence, but he does not give an explicit expression for them. Okay. But he studies something like this on homogeneous space in general.
Oh, okay, fine. So, Andres, you can ask your question.
Please, Andres.
Hi, Carlos. How are you?
Hello, I'm fine, thanks. You?
Fine. On the last proposition that you say today, this subspace L, is possible this subspace be a subalgebra for the, I mean, something that you construct from subalgebra of the Lie algebra, or it's just a subspace?
For me, it's just a subspace. I never try to look it as a subalgebra or something like this.
Okay.
Yeah.
Okay, thank you.
You're welcome.
So let's thank again Carlos. Okay.
Thank you.
And we come back to the next class on Friday. Okay.
Thank you.